Okay, so in this video we will solve this RC circuit that looks like this. Let's say the resistance is 1K, the capacitance is 47 microfarad, and the source voltage is 5 volt DC. Well, so in this video we will find the capacitor's voltage, and also we will find the current across this circuit. And you see we have a matlab code here where R is 1K, C is 47 microfarad, this VDC is 5 volt, and also we have a V initial. What is V initial? V initial is the initial voltage of this capacitor. So V initial is given the initial voltage, that means when time is equal to 0 the capacitor's voltage is 2 volt. So now we have to find the capacitor's voltage equation and we will plot that in time domain. Okay, so let's start. So first of all I have to write the equation, current equation across this capacitor. So we know I is equal to C dV by dt. Again we know that the current across this resistor is simply Ohm's law. So I is equal to Vs minus V divided by R. Well, so now we have to simplify this equation, and if I do this I will get dV by dt plus 1 by RC into V, Vs divided by RC. Pause this video and you can and do it by yourself. And then we have to transform this equation into S domain. That means we will do a Laplace transform here. And how to do Laplace transform? This dV by dt will become as Vs minus B0, right? And this V0 is actually V initial in our code. And then we have 1 by RC, Laplace transform of the voltage. Then let's see what is this Vs. So this is the Vs. So this is the Vs, and Vs is equal to BDC ut. Why? Because we have switched on t is equal to 0. That means before the time was 0, this Vs was equal to 0, but after the time t is equal to 0, this Vs is equal to VDC. And we know that the Laplace transform of ut is equal to 1 by s. So the Laplace transform of this thing will be equal to BDC 1 by s. Well, so let's do this here, BDC 1 by s. Okay, so now let's simplify this equation. I think I have made a mistake here. This is not Vs, this is actually V. So V is equal to BDC divided by RC 1 by s plus V initial divided by s plus 1 by RC. Well, so let's now go to our code. So we have used the clear variables here because we have written a lot of codes above, and we have used a lot of variables here. Now we want to clear that variables, we want to remove the variables above, so we have used a clear variables command here. It's a good practice to do this. And then I have written a sims function to make this s and t to symbolic variables. These are not double variables, these are symbolic variables. Then R, C, BDC, V initial, and then we have made this V, which is simply equal to this. That means we have made this equation here, and then we have used inverse Laplace built-in function to find voltage in time domain. Okay, so now let's plot it from 0 to 1 second and let's see what happens. This is the equation and the plot looks like this. So you see the initial voltage So the initial voltage is 2 and the final voltage is approaching 5. It cannot become 5. Theoretically at t is equal to infinity it will become 5. Well, so now let's find the current of that capacitor. So we know that I is equal to C dV by dt. So this is the current across this capacitor. Also this is the current, as resistor and capacitor are in series. So this current is flowing through all the elements. Well, so now let's take the Laplace transform of I and we will get capital I. Then Laplace transform of this thing will give us as V minus V initial. Well, so now let's make this equation in our code here. So I is equal to C, then S into capital V minus V initial. Okay, so now we have to write, here we have to write star as B minus B initial, and now we have to make an inverse Laplace transform here. Capital I, this I is in S domain but we want to convert it into time domain, and let's take the result in I variable. You can see that. Well, so now let's plot this I. Instead of V, let's write here I, and now this is not voltage, this is actually current. Well, so now let's plot this portion. So this is the equation for the current, and so this is the current equation. You see, at the when time was equal to 0, this capacitor's current was 3 milliampere, but as the time progresses the capacitor's current is tending to become 0. And you can also find the voltage across the resistor. How you can find this? Like, this is the voltage across this resistor, which is simply is equal to IR. So in similar technique you can find the voltage across this resistor.